Okay, welcome everybody. So in this video, in the next several videos, we are going to explore the idea of what is a vector space, take a look at some examples, encounter examples of spaces and operations that may or may not satisfy the properties required to be a vector space. So let's first define what a vector space is. So a vector space consists of three different things. First of all, we have a non-empty set of objects that we typically denote V for vector space. And these objects, they can be vectors that we've been working with, or they can be more abstract things. So we'll see various examples where the set of objects we're working with may be vectors, may be functions, they may be matrices. But along with these objects, we define two operations. One is called addition and one is multiplication by scalars. So we need to define what does it mean to add two things in this set. How can we define adding two of the objects in the set? And then how do we describe multiplying an object in this set by a scalar? And once I have a group of objects, a set V, along with some addition operation between vectors in the set and multiplication by a scalar, then as long as these operations satisfy a list of properties, then we call this a vector space. So let's think about some of the properties that would be nice for this to satisfy. The first property is we would like to say if I take two vectors u and v in the vector space, then when I add them together, whatever that means, we get an object which is also in the vector space V. So we would say we want to make sure that the operation addition is closed so that when we add any two vectors, we get a third vector which is also in the vector space V. The second property is we want addition to be commutative. So if I add u to vector v, that should equal what I get when I take v and add it to u. Third property would be we want to require that addition is associative. So u plus v, then adding w is the same thing as if we first add v and w and then add u to that. Property 4 that we are going to require is that our set V contains a zero vector that we'll denote with bold 0. And what it means to be this zero vector, it tells us that if we take any vector u, all vectors u, and we add 0 on the right of it, then we get u back. And by combining this property with what we know about addition being commutative, then it also follows that if I take 0 plus u, I should also get 0 back, since 0 plus u should equal u plus 0, which is u. So basically, there's a vector in this set V so that when I add it to any other vector in the set, it does not do anything. The result is the original vector in the set. Property number 5 is the additive inverse. So for any vector u in this vector space V, there exists some other vector, the additive inverse, that we'll denote with minus u. And note, this doesn't mean necessarily minus 1 times the vector u. This is some other object that will denote minus u, so that when I take u and add minus u to it, we get the 0 vector back. So these are the first 5 properties that mainly work with the addition operation, properties that addition needs to satisfy. We have some additional properties about scalar multiplication, and so we want to make sure that if I take any vector u in the vector space and any scalar c, then c times that vector u is going to result in another vector which is also in that vector space V. Property number 7 is the distributive property, in the sense that if I take a scalar c times the sum of two vectors u plus v, that is equal to what I would get if I took c times u and then added c times v. So that is giving us some relationship between the two operations of scalar multiplication and vector addition. And we have a second distributive property which says if I am adding two scalars, c plus d, and then multiplying by any vector u in this vector space, that must equal c times that vector u plus d times u. Property number 9 is the scalar multiplication is associative. So if I take c times the vector d times u, it's the same thing as if I first multiplied the two scalars c and d and then multiplied by the vector u. And if you're looking for even more properties, then yes, we've got one more property, the final number 10 property, which is that we have a multiplicative identity, namely there exists some scalar, usually 1, denoted with a 1, so that when I take this scalar and multiply it by any vector u in the vector space, that it doesn't do anything, and what the result is going to be is that same vector u back. So here are 10 properties that this set V, along with these two operations that we define, must satisfy. And for any set V that has these two operations that satisfy all 10 of these axioms, we call this space a vector space. And we'll see that these properties are going to work really nicely with some of the linear transformations we've been studying so far. So let's take a look at some examples to illustrate what things may or may not be vector spaces.